Roundtable panelists and our moderator, Juju Chang.
Well, good morning, everyone. It's so nice to be here at Maples Pavilion. Welcome back to the farm. I graduated back in 1987, so it's been a while. But as your moderator, my job this morning is to introduce and set forth this distinguished panel of experts on the brain who are seated in front of me. We're going to start by John Hennessy, who is we all know and love here in the Stanford community as our 10th president. He joined the faculty back in 1977 and has taught both in the School of Computer Science, Electrical Engineering. He became dean of the Electrical Engineering School as well as chair of computer science. He's launched a number of pioneering interdisciplinary institutes here at Stanford. He served as provost. He's written international textbooks. He served for a time successfully in the private sector, but we're so pleased that he is at home here at Stanford. Seated stage left, as I like to say, is Professor Frank Longo. He is a professor at the School of Medicine, also chair of neurology. He studies the causes and effects of dementia. And if you look at the list of publications under his name, I can't pronounce half of the title, so I will spare you. However, he does look at the issue of neuroplasticity, and he'll talk about how that affects all of us. But when I asked him what his brain-boosting personal regimen is, he said three things: exercise, exercise, exercise. So we'll dig into that in a little bit. Welcome to Frank.
Thank you.
Jill Bolte-Taylor, you may know as Time Magazine's one of the 100 distinguished people, according to Time. She was, as you may know, 37 years old, a Harvard-trained brain scientist studying schizophrenia and mental illness when she suffered a massive stroke. And her 8-year recovery from that turned into an incredible book called Stroke of Insight. She has appeared on Oprah. She gave an incredible 18-minute talk at TED, which became the second most watched TED speech of all time. And you'll see that she has studied the brain from the inside out, and we're so thrilled that you're here. And when I asked Jill, what is your personal brain-boosting exercise, she said, sleep. So we'll get into that. And Carla Schatz is a professor of biology and neurobiology. She is the distinguished director of BioX, which is a organization that started and was launched here by John Hennessy that also really is a pioneering interdisciplinary look at biosciences. She studies autism and schizophrenia and does a lot of mice studies in a lab. Wouldn't it be nice to have a lab named after yourself? The Schatz Lab here at Stanford. And when I asked her what her personal brain-boosting activity is, she said, well, I don't have time for everything. Oh, yeah, well, I meditate, I do yoga, and I eat blueberries just about every day. So we'll look at that. Thank you, Carla, for being here. And to my right, stage right, is the distinguished Bob Woodruff, who is a dear friend and colleague of mine at ABC News. He is every bit the dashing foreign correspondent, having been based in London for ABC News. He came back to succeed Peter Jennings as anchor of World News Tonight. And 1 month after being named the anchor, he was hit by a roadside bomb in Iraq. And the subsequent traumatic brain injury and coming back from that has made a major shift in Bob's life. He was in a medically induced coma for 36 days. And coming back from that traumatic brain injury has been documented in an incredible book and a loving one that he co-wrote with his wife, Lee Woodruff, as well as an hour-long documentary that aired to much acclaim on ABC News. He has gone on to found Stand Up for Heroes, which is a nonprofit that deals with veterans from the wars in Iraq and Afghanistan. I want you to talk a little bit about that. And I happen to know that your brain-boosting activity yesterday was a long run around campus where he said, "Wow, girl, you're lucky to have gone here." So thanks for coming, Bob. But of course, I want to start with John Hennessy because obviously neuroscience is a priority here at Stanford. I want you to share with us your thoughts, John, if you will, on why it's a priority here and why it's such a classic example of interdisciplinary research.
Well, that's a good point, Juju. I think we see this as the great new frontier for research. And if you think, let's say an analogy, think about the discovery of DNA now some 50 plus years ago. And we're still just understanding how to use those insights in medicine and treating people, developing new therapies, and the science. We really don't understand all the science yet. Well, we're not even near the DNA discovery for the human brain. We're far before that. So we have before us lots of deep insight to gather about the brain. And from that insight, I believe in the long term will come better treatment for Alzheimer's, for Parkinson's, for schizophrenia, for people who suffer from injury, whether it be stroke or other injury. It's also highly interdisciplinary. And the faculty involved range from the medical school, where the neuroscientists are, and neurosurgeons, psychiatry, to people in engineering who think about what we might actually develop as new therapies and new devices to help people who have injuries or brain damage, all the way over to law or economics, where they're interested in how does the brain make decisions, how do people think, and what insights could we use from a better understanding of the human brain in thinking about those issues.
Carl, I want to kick off with you a little bit and really mix up the discussion, but you are doing a lot of research on mice, looking at why, in fact, it is hard for an old dog to learn new tricks. Why is it that the brain is more supple and more able to learn when we're younger? Give us some insights into your research and what implications it has for all of us.
Yeah, the old dog, new trick story is a story of our lives in a way, and certainly mine. I'd like to learn some new tricks. And I've always wondered why it is that it was so easy for children. They seem to learn effortlessly. And they can learn languages effortlessly. And I know from my own experience, my own poor experience, how difficult it is to learn a language after, puberty. I mean, I learned French when I was young. I don't remember the words, but I can speak it. And it's amazing what is going on in the brain of children that might be different from what's going on in the adult brain. And those are the kinds of things that I study in the lab. And one big thing that's happening in children's brains is that wiring is still happening. And so the nature of learning in children is very, very different from the nature of learning in adults, where most of our wires have been established both by a combination of genes and also experience. But in children, they're still experiencing everything. And that is actually laying down many, many new connections. And what we want to really understand is, how does that happen? Because, wouldn't it be nice if you could someday take a pill and allow your old brain to revert to that early learning period? Anyhow, when I started my career many years ago, I wanted to just understand the child's brain and this mechanism of learning. Now, as I get older, I want that pill, and I want it really soon.
But does that mean as parents we should have our children take the piano lessons and the skiing lessons now when they're younger, or is there a way that later we can perhaps include learning for older folks who are perhaps in the audience?
Yeah.
I don't know. I only have bad news. No.
I think there are ways. One of the additional fascinating processes, the key word here is pruning. So we're born with many more connections than we have as adults. We're born with the wiring to speak fluent Mandarin. And as we age, if we don't use those connections, they're literally pruned away. Now, the upside of that is to create efficiencies, because we don't want excess wiring, and theoretically we're more efficient without wiring we don't need. So one of the key parts is using the wiring and stabilizing it. Once that wiring's pruned and gone, we no longer have it as adults. But I'm a great believer that we can attain some of that plasticity in adults and establish some new connections as adults.
Well, that's what you're looking at, the area of Alzheimer's and the other causes of dementia. And just share with us some of the most promising research that you're seeing in that area.
Well, so the problem that we see in many forms of dementia, including Alzheimer's happens to be the most common form of dementia, accounting for about 2/3 of all dementias. One of the key processes in Alzheimer's is that the synaptic connections, we have 100 trillion synaptic connections in our brain, we start to lose those connections. And so the goal is to maintain those connections or to gain them back. I mean, that's the real focus there. And it's possible that the memories we've lost are because we don't have those connections. If we can get those synaptic connections back so the neurons can communicate, we can actually recover some of those memories.
That segues beautifully to Jill, who has developed all sorts of new pathways after your stroke. Share with us some of your experiences and some of the thoughts on where neuroplasticity is right now.
Well, I love the whole concept of neuroplasticity. Of course, I would not be sitting here talking to you. On the morning of my stroke, the hemorrhage was so large that I could not walk, talk, read, write, or recall any of my life. So I describe myself as an infant in a woman's body. And the process for me then was allowing time for the traumatized cells to settle down, for surgery to happen to remove a blood clot the size of a golf ball, allow that trauma to settle down. And then it became a focus of which circuits, as a neuroanatomist, I think in circuitry. And then the question was, which circuits did I want to focus on in order to be able to bring those back online? And of course, the most important one for me would be language, because without language, I would not be able to interact or communicate with fellow man. I would never have a voice that could be heard. I could never tell the story of what had happened to me as I shifted away from being one way in the world and running certain circuitry that was dominant into being another character who was completely different, with a completely different perspective of what's going on inside of my mind. So for me, I look at circuitry and it's a matter of energy. If I was going to focus on it and put my energy into running the circuitry, we know that we have reverberating circuits. And the more energy you put into a thought, the more you think a thought, the more that circuit's going to run automatically on its own.
So give us some examples of the therapies that you think are most exciting in terms of building those new neural pathways.
Well, I think for me, it's a matter of looking at your brain and figuring out what circuits are you already running. There were certain circuits that I didn't want to bring back online. Anger, for example. The first time The first time
the first time that I felt anger, that it was, what is this? I felt my chest get tighter, my jaw clamp, the furrow in my brow. I just was, the anxiety inside of my body. It felt terrible, but I had no word for it. And so I'm describing this to my mother, and she's saying, Jill, that's anger. You're feeling angry. And it was like, ooh, why would anybody want to do that? Yeah. So it was like, okay, well, what is at the core of my anger? Because it was clear that what was bringing me, triggering that circuit, wasn't the anger. The anger was the circuitry inside of me, and it was like, all I have to do is get rid of the triggers and not allow that to be out for people to jump on, and then I wouldn't have to run that circuitry. So for me, it became very mindfulness. What do I have to do in order to pay attention to how I feel inside of my body, and whether that's something I want more of or less of? Bob, I'm wondering how much of this you can relate to, and I want you to jump into, we all know that 20% of veterans coming home from Iraq and Afghanistan may have traumatic brain injury, and clearly when you fold in professional athletes and high school athletes and the repetitive concussions that are out there, traumatic brain injury is a huge area in need of study. Share with us some of your personal experiences. Dive in on this idea of rebuilding pathways.
Well, first of all, one of my goals today is to make Jill furious so she can snap in the middle of this, just to show that she's dead wrong. Now, but what happened with me, of course, was there was a 155 millimeter IED explosion, really about 20 yards off to the left over here. Which, when that blasted, the shake of the the power of the air first completely knocked me unconscious instantly. That was before the rocks and the metal pierced and shattered this part of the jaw, shattered my scapula in the back. Some of them passed all the way through, past the veins and the arteries, the trachea, the esophagus, missed miraculously all of them and just came all the way to the other side and just 1 millimeter away from piercing through the carotid artery on the other side, which they got out later. I was just knocked out instantly. What we did know at that moment, though, is that literally I fell back into the tank. My team, my cameraman, my sound man, my producer, were all downstairs. They pulled me down. They eventually stopped the bleeding, which was pumping out of my neck. Everyone's thought for sure I was going to die. We were with the Iraqi and the U.S. military working together at that time in 2006. And they got out, and when they came to get us out of the tank we were in, there was gunfire from all four corners from the insurgents that had blasted this off. They somehow ended that. They got us in, put us in another Bradley, got us down the road to a helicopter. Helicopter went down to Baghdad, stabilized us down there, got us to a second one in Balad, which is the main medical center in Iraq at the time. Did a craniectomy, took off this skull of my head 16 centimeters so the brain could expand without being pushed up against the bone of the skull, so it cut off all oxygen. Without that, who knows, I probably wouldn't be sitting here right now, certainly speaking any language whatsoever. Then they got us from there up to Longstuhl and then back to the United States. That was about 72 hours after the blast. In fact, after that explosion and those getting us a mile down the road in a Bradley into the helicopters, we were up to Balad for that craniectomy within 47 minutes.
It's incredible. And I know that so much of what happens out in the field is now being transferred to hospitals stateside to help people with traumatic brain injury.
I think sometimes one of the upsides to the war is the medical advancements that we got. But the point really is, though, is that we are saving lives more than we ever did before. But the big mystery and the curiosity is how can we fix the brain? Because in my particular instance, there was I was not pierced by a bullet. We don't know exactly in the brain. It gave me very traumatic brain injury. Because mine was hit on the outside of the skull and then shake the brain around inside against each back and forth like this. So exactly where the damage is not completely clear. In terms of languages, what the studies have shown is about age 6, they think, the language that you study Chinese when you're born along with English, maybe French, whatever it may be. Those languages, there's no translation that's going in your brain when you use those particular languages. So you're speaking your Spanish you grew up with, along with your English, you go back and forth with you're not translating, thinking in one language and then translating to the others. Even when you feel fluent, the ones learned after 6, actually there's a slight translation. So they tested mine to see if I had studied French and some Chinese before this all happened, and so they tried to test me on those other languages too, and it was no better. Because largely I was not a particular part of that brain. Because they think it's one, you learn it younger, it's in one part of the brain, and the one you learned later on is a different, so if you get hit in one spot, maybe it's not so bad a language. In fact, I met one guy who exactly the same thing. A guy that was beaten up in Tiananmen Square they did find out that his Chinese was better than his English after they did some tests on that, even though he was hit. So they were saving tons of lives, but we got huge numbers of PTSD, et cetera, because their lives are saved, but they have damage to their brain because of the shaking around of an IED explosion.
I think we're all sort of walking miracles, but I feel very honored today that we have two such true miracles right with us here. And I couldn't resist because you're talking about learning languages and everything.
I was dead wrong, wasn't
No, you're so right. I was so impressed. I thought, what can I add? But one thing that's amazing is studies of the way children learn language is that apparently we start out life as citizens of the world, in that we can in fact learn many, many languages without an accent. And part of the reason is that the brain needs to practice and hear. It needs experience really early. And as Dr. Longo said, that actually changes the connections as they're forming in the brain. And we keep a lot of connections that allow us to distinguish later in life the R from the L and so on. And if we don't use those connections, it's really use it or lose it. So what happens is those connections actually get pruned. And so we actually lose those connections as we become more skilled in other areas. And one thing I think is really exciting about the future for brain research and for therapy and for plasticity is that when you think about it, losing those connections during our young lives as we experience the world, it's not that different, maybe, from losing connections in aging, in abnormal aging, in Alzheimer's, for example. So if we could understand what the process is that lets us lose connections during early life and grow connections and strengthen them, maybe we would actually learn something new about treatments for Alzheimer's and other disorders of the brain, neurodegenerative disorders. So it's amazing that studying, the developing brain might really help us someday understand the aging brain.
Sure.
So,
Frank, I saw that you wanted to jump in, but I also want to ask you to sort of comment on what I jokingly referred to about exercise, because clearly that is one of the areas of research that's showing a great deal of promise in terms of boosting brain power.
Sure, exercise is important. And to get back to President Hennessy's point, we're at the early, exciting stage of the field of neuroscience. And I look back to the 50s when the heart-lung machine was invented and the field of cardiac surgery just blossomed and took off. We're at the early days of neuroscience now, and the experience Bob had with the head trauma 10, 15, 20 years ago, this was a black box. We had no idea what was going on. And we're at early days, but this black box is starting to become visible, have visible workings inside. We now understand that with head injury, we can lose some of the axon connections. We can lose some of those synaptic connections. The more powerful brain imaging is giving us insight. And so we're having glimpses that we can act on in terms of understanding mechanisms. For example, there are very powerful growth factors, protein growth factors in the brain that can determine whether a synapse persists or whether a new connection persists when we learn something. And one of those growth factors, interestingly, is called brain-derived neurotrophic factor, BDNF for short. Interestingly, the level goes down as we age. It especially goes down with Alzheimer's disease. And guess what boosts the level of BDNF, this precious, potent protein? Exercise. So when people or mice exercise, the BDNF levels go up. So it's no longer a black box. We now know that BDNF exists. We know that it goes down in aging, goes down even more in Alzheimer's. Exercise can boost it. My own group here at Stanford is working on creating molecules, little molecules that could be drugs someday that do the same thing BDNF does. I don't want to say we have exercise in a bottle. I would exercise
Let me
instead.
prescribe some exercise for you.
So I think so exercise is an incredibly potent treatment for promoting plasticity, the ability to form new connections, and maintaining the connections that we have.
I want to pick up, Carla, on what you were saying about use it or lose it, because frankly, my Korean is terrible, even though that was the first language I spoke. And yet, John Hennessy's wife shared with me that he's a big reader and that he does the New York Times crosswords puzzles. And we all know if I do Sudoku, that'll help. So the question is, what is it about reading and these other mental exercises that help, with each of us? Jill, feel free to jump in.
Well, for me, it was, again, it is the use it or lose it. And the more you use it, the more you exercise that circuit. My mother is a big crossword puzzle person, and I say, well, your crossword puzzle circuitry is really great. Right. What about the rest of the stuff going on in there?
Because it's actually about learning something new.
It's about something, yeah. And crossword puzzles are learning something new because they're language, and they do relate to society. And so she always moans poems when the New York Times is relating her to culture, but I say to her, this is good for you because you are making new associations, you're expanding what you're actually doing here. But there are all kinds of activities that we can do inside of our brain, so I'm a true advocate for do a little bit of a lot of things and mix it up and don't do the same routine. And when you look at us as normal U.S. citizens, as we get older, we try to simplify our lives and we routinize ourselves. Well, to me, what that's saying to the brain is we don't need you to be real complicated. We're trying to simplify, simplify, simplify. Well, maybe then I'm going to simplify myself to the point where I'm not challenging my neurons at all so that they're not reaching out for new forms of stimulation. So I encourage everybody, flip your calendar upside down and just like, you can still figure it out, but you have to work a little. That's what we need to do. You need to work a little. It wants new, novel stimulation.
So just to torture the old dog, new tricks metaphor a little bit further, we actually, as old dogs, need to continue to learn new tricks. Yeah. Bob, what, if any, sort of, brain therapies do you find helpful?
That's interesting. I was going to say that I think people often ask the question, how long did you do therapy, speech therapy, occupational therapy, physical therapy? And I didn't really do a lot of it. I did it for a certain period of time to the point where professionals like you, scientists and doctors would tell me, here's what you want to do. Like that, read, have good conversations, exercise, flip the calendar over, whatever it may be. And then you can figure that the best thing to do is in your regular life, just to be able to do this without having to go down to the hospital or the therapy center and do that kind of thing. So I tell people, no, I've not officially been under the definition of therapy, but if you do engage in those kind of things. With the brain, you're talking about Alzheimer's. My mother has really bad Alzheimer's now, and every day getting worse and worse, and I'm sure there's some genetic aspect to it, which I know that Carla told earlier. And then also given the fact that because of brain injury, you're also more vulnerable to Alzheimer's as you get older. So I got kind of the double whammy on that one. So we don't know exactly what to do to stop that, but exactly what you're doing. Because when this happened to me, in a way, I have now had the experience that my mother's going through. Not many of us can say what it will be like to have Alzheimer's, but I could not understand when I woke up. I couldn't remember the names of my children. I couldn't remember the names of a single state in our country. And for some strange reason, some names, it didn't make sense. Some longer words I knew and short ones I couldn't remember. They were just thrown out. Some that didn't make a lot of sense. I couldn't remember the name George Bush, That's simple words. And then by some reason I could remember, this is not a political place, okay? But I could somehow remember, Mahmoud Ahmadinejad or something like that. So none of it makes sense, but it's just some strange things. And sometimes when I see words, I know how many words how many letters there are in a word, but sometimes I confuse the order of them. So if you've got 3 or 4 synonyms for a word with almost the similar numbers of letters and sharing a lot of the same letters, then I confuse them up a lot. It's like Verizon and Viagra, very.
Right. that could be an interesting advertising campaign.
Yeah. Which one do you buy?
Right, exactly.
Yeah.
I have a question for Jill, because one of the things that I found amazing about your TED video is that you remember what happened when you had that stroke, and you were able to relate how you felt, and that's amazing that you could remember that, because then you say at the same time you couldn't remember lots of other things.
Oh, yeah. Well, I lost language, and I lost the ability to see boundaries between things. But when you think about any of the major memories in your mind, you're running a video, and the video was my right brain, and I didn't lose that. I could have, a couple of weeks after the stroke, I could have sculpted for you an abdomen because I had a right brain, and the right brain is in relationship to the body, an association in the big picture of everything, how it's related. I didn't have the left brain that would say the stomach is divided into 3 parts, and these are the names of those parts, because I didn't have that division. At the same time, I didn't have the division of where did I begin and where did I end separate from the air around me, and I didn't have the language center that said I am an individual. So I shifted into the big picture of everything, which is right there in my right hemisphere perception of how do I relate to the bigger picture, and then I have this beautiful left brain that takes it and divides it up into detail detail and allows me to relate to the external world.
You had said earlier, Jill, that you're so in love with the right brain that you see cuts in funding for certain types of education as a bit of a travesty.
Yeah, it is. When you stop and you think about budgeting for educational systems, what are we cutting out? We're cutting out music, the arts, and physical education. These are things that actually feed what's going on inside of our right brain. And it's really important to me. I'm not an advocate for the right brain or an advocate for the left brain.
I
am an
suspect you're
advocate
fond of your left brain
I
as
am.
well.
Without it, I was totally non-effective. I was in a blissful state of la-la, but I was totally non-effective as a human being. So I'm really all about the balance of the brain and how do we look at what we are as living beings and recognize we have a big picture way of looking at the world. And when it comes to Alzheimer, one of the things that I was thinking as you were speaking, you're in the lab trying to come up with molecules that can help fix the mechanics of it. But what is it like to actually have that experience? And do they care? And so ultimately, when people contact me and they say, my mother has Alzheimer's, she hasn't communicated with me for 3 years, I say, well, when you go in, what do you do? And they say, well, I sit and I talk to her, or I tell her this, or I read to her, or I read the paper. And it's like, well, why don't you just go in, nudge her a little, and grunt? You know, go into her world. Connect with her. It's not about how do I get you to understand my reality. It's how do I come and be a part of your reality. It's what we do for autistic children. It's what we do for infants. It's what we do when we try to help compassionately be open. We have to go to your level in order to teach you or to connect with you.
Do you know that's better therapy for her to do that? Does it improve them a little bit? I mean, do we, like our children, for example, our children just grump too. Should we just go and teach them something, or should we just grunt at them too?
Well, I think in the beginning you ought to grunt at them and you ought to gain their trust. It becomes about trust. The amygdala is where all the information is streaming in through our sensory systems and going to our limbic system. The amygdala right now asking the question, am I safe? And it determines that based on how much of the information feels familiar. And if you feel familiar to me, then I feel safe with you. Once I feel safe with you, my hippocampus turns on and I can learn and memorize new information. I can actually engage with you. But the first thing for anything, and I'm sure it must have been true for you, when I was a Harvard doctor, and then I became an infant drooling, and my world was unfamiliar. And simply because of that, I felt like I was an alien in a space that was dangerous. And the people, Dr. Ann Young, who came to me and looked me in the eye and touched me gently and drew me out and just treated me like, I know you're wounded. You're wounded and I'm here to protect you and to help you. That made all the difference in how I received somebody's caring. And I tell professionals all the time, if you want to connect with me, if you want to teach me, you have to be a safe space for me first.
Frank, I see you want to
we have two beautiful examples here of recovery, and we can ask what it was like to be in those states, and each of you are so articulate in describing that and have recovered. For an Alzheimer's patient, unfortunately, no one has ever recovered. It's one of the areas in medicine that we have actually a treatment has a 0% chance of working currently. But we'll change that fairly soon, I think.
I admire your optimism.
We will.
I do.
And I'll make a bold prediction here. So we study Alzheimer's mice. They've lost many of these synaptic connections. They do terribly at memory and other tests. And believe it or not, we can do a neurologic exam on a mouse with Alzheimer's and test its memory. When we treat them with our experimental molecules, they can regain those synapses and regain memory. So what I predict is when these make it to human, when we can reestablish those synapses in a person that's had Alzheimer's, we can then ask them, what was that like? And then we'll know. And that'll be a great day.
And Jill, there are moments in your TED Talk where you talk about, then my left brain came back online and I had this moment of clarity, and then I went back into La La Land, and it sounded to me almost like somebody with Alzheimer's. Like somebody, because we all know people with Alzheimer's go out of it and then come into it, and clearly there are moments of clarity.
There are great fluctuations, and on a good day, it inspires us about what could be if we could capture that, make it a little better, and keep it going in the right direction. I think much of traditionally, the way we've learned about the brain are through these injuries, whether it's a stroke or brain trauma. If the left part of the cerebral cortex is damaged and the function is lost, say an element of language, we think, okay, language lives there. What's exciting now is we're developing the technologies, and a lot of this is being led at Stanford, where we could see brain circuits functioning in a living, normal person. And the computer science and physics communities here contribute to the imaging developed at Stanford. So my colleagues are developing ways of looking at these circuits in just an uninjured person and getting those insights without having to deal with the injury. And there are nodes and hubs in the brain running continuously, creating these functions, and we can see it.
So this is a very critical area because there are limits to how far you can go with animal models. You can do certain things with mice, you can test certain memory aspects, you can do the same thing with monkeys, and there's been a lot of research with monkeys that's been done. But language is such a core part of what it means to be a human being, and of course those are animals that don't have language. So figuring out how we can move our research to work on human beings without, well, what we do to mice and we do to monkeys, people are reluctant to let you drill holes in their skull and put probes in. So we've got to find a way to be able to do that that's non-invasive, that doesn't destroy functionality and ability, and understand how the human brain works, because it's much more complicated beast than these other animals.
And yet, John, to pick up on the idea of drilling holes and looking inside the brain and seeing a placebo effect, last night you two were in the midst of a conversation about placebo effect, and you were saying that researchers actually did drill holes into people's skulls and not perform any treatment, and there was a powerful placebo effect.
So we deal with placebo effect quite a bit. So when I'm in the neurology clinic, my families and patients are on the internet for hours, and you can find 100 cures for every disease, and so it's quite frustrating. And of course, what our response is to apply some scientific rigor to these so-called cures, and we deal with the placebo effect because many of these treatments are done in open ways. There's no blinding. People know whether or not they've got this magical treatment, and so we're always worried about placebo effect, and this was really brought to bear in Parkinson's disease. So starting back in the 80s, people were transplanting embryonic stem cells into the brain of Parkinson's patients, and in Parkinson's, neurons are dying that regulate movement. And so the goal was to replace these neurons, and the patients were responding. Their walking was better, their tremor was going away, so we thought this was exciting. And so the question of placebo came up, and it was an ethical debate. How can you do a placebo brain operation on a person? And so, but people said, what are the ethics of doing a therapy if we don't even know if it's really working or not? So a trial was actually done, a formal trial, where a Parkinson's patients volunteered to have a burr hole drilled in their skull by a neurosurgeon. And the neurosurgeon either injected real stem cells or pretend injection, and the only person in the operating room that knew what was being injected was the neurosurgeon. So the neurologist evaluating the patients, the nurses, the patient, the family, nobody knew. And guess what happened? The stem cells and the placebo injection had the exact same effects on those patients. So it just gives the power of a placebo effect. So we really have to pay attention to that.
But is that
Could be
not
the
the power
drill,
of the
Frank.
brain?
It could be the
It could be
drill.
the drill.
Maybe it was the
exactly.
drill, yeah.
It could be the drill. But is that not the power of placebo? And that's
right.
what you guys were
That's
digging
exactly
into
right.
last night, which I thought
That's
was
right.
so fascinating.
Because then you have to ask the question, I have to ask the question because I'm not in the lab and I don't care whether it's this or that. What I care about is that this and that. So what about the power of the mind? What is the power of hope? What is the power of prayer? What is the power of meditation? What is the power? What is the placebo effect? And how can we turn that into part of the solution instead of just saying, oh, well, it was just a placebo effect, it doesn't count? Because something does count in there, and it's a natural biological mechanism. And, you know, being a stroke survivor and having recovered all of my abilities, I had a little bit of speech therapy. I had no occupational therapy. I had no physical therapy. And yet, look at this. And this was done consciously by somebody who thought about neurocircuitry and the ability of the brain to recover itself. And there's no question in my mind that I'm here in full capacity because I believed in the ability of my brain to heal itself. If anything knew what it needed for it to recover, it wasn't going to be my physicians, it wasn't going to be my therapist, it was going to tell me, which is why I'm an advocate for sleep. Because one thing we don't do in this society is sleep. How many of you are sleep deprived? Look at those hands. Now, I'd like to do a study on recovery and sleep. You know, it seems to be the simple things. How do we work with integrative medicine, not just traditional classical medicine, but with the integrative tools that look at what is healthy and how do we make that healthier in order to bring the whole animal online. So I believe doing both.
Right, and there is study after study that shows that children have better cognitive function after an extra hour of sleep. And so there is a big body of evidence that suggests that that's helpful.
So I was going to say, let's go to the healthy brain then for a minute, because this is about the healthy brain. This ability, the placebo effect, sleep, and what John said I think is extremely important, that we have to have much better methods for understanding non-invasively what's going on in our brains, now, without drilling holes. And I think there's a lot of promise and excitement for this. And it really comes to this issue, too, about being able to say that, well, the amygdala made me do this, and then it was the hippocampus. I'm always amazed when I watch PBS programs on the brain, how wonderful they are. And I'm always amazed as a neuroscientist. I always go to myself, gee, I didn't think we knew that much. And I don't think we know that much. We always make it sound as if it's so simple. It's the amygdala, or, it's use it or lose it. So I think we need to learn much more about what's happening in those circuits, online. Wonderful challenges for science and for technology. And this is where I think Stanford can make a difference, because the brain is the most complicated organ. It's one of the most it's probably the most complicated computational machines that we can imagine, because it is changing online, and the hardware is changing online, not just the software. And we have to have methods, not only the genetic method and the molecular biology method and the clinical methods to approach understanding the brain. We really need the engineers, and we need the computer scientists and the physicists and the statisticians. Everyone really can contribute to our understanding of this extremely complex machine. So it's a very exciting time. But I also want to add just a little bit of concern, because I feel that it's also a time of great challenge for us in this country and in the world as it becomes harder and harder to marshal the research funds that are needed to really attack this very complex problem. And I hope we don't forget that the advances that we've made in the cure for cancer, for example, and cures, came because we invested a huge amount in those problems. And in the same way, it would be nice to be able to make that investment so that we really could understand, first of all, what the two of you managed to do to affect your own recovery. How did you do that? And how can we help so many other people?
Well, it segues so nicely to Bob's Stand Up for Heroes, because he works in that community and helping others recover from traumatic brain injury. So, Bob, share with us some of your insights on that score.
Well, I think we've learned so much more about the brain. I know that I sometimes tell the story that at that point when we wake up, and I think in terms of depression, you're talking about excitement, you're talking about change in life. I think when people wake up after realizing, wow, they're alive, after these troops that get rushed out, they're unconscious, and then they come back. I think in those ICU hospitals, they are pretty happy. And then as time goes on, they become major psychological problems as they realize that their life has changed. And the big question, this is along what you're saying, is what is it about the psychological aspects versus the physical aspects that are affecting the brain the most? We do know that, I know when my kids were talking to me, my friends were reading to me when I'm recovering, there's no scientific proof, but I think absolutely that sped up the recovery to some degree. For the same reason you talk about next to your mother, just kind of, getting on her level. I think that's a psychological impact. We do, I know that some of the studies in terms of education, a lot of us memorizing things, being sort of told what to do, that eliminates our creativity. Something that's more creative will actually improve the brain. But is it actually changing the brain physically, or is it changing something psychologically? And that's what we don't know yet, right? I think the assumption before was we have our cells of our brain just are on decline, right? We're never going to need more. But do we have now proof, now that we actually can get more cells in our brain in the hippocampus than we did before?
So it's interesting. We hear a lot about stem cells. And what's fascinating, there are one major part of the brain and a few major areas of the brain where we have our own stem cells in the adult brain. In the hippocampus, the part of the brain critical for memory and acquiring new knowledge, has its own stem cells. And every day they're making some new neurons. So we're making new neurons every day. Now, this ability goes down with age, but it goes up with cognitive stimulation. It goes up with exercise. So we have some control over it. So as I hear your story of recovering, this is what I'm thinking of. These synapses are forming every hour. We're forming new synaptic connections continuously. As we all sit here, these synapses are reaching out, coming in contact. They'll last for 15, 30 minutes. And then what determines whether they'll persist or not? It's whether they're used. So as you had your friends and family read to you, as you pushed yourself on these languages, I think you kept a higher proportion of these brand new synapses than you otherwise might have, and also with your recovery, Jill. And so I think that enhanced your recovery. We were talking about placebo effect. I think placebo is incredibly important. I think you harnessed your own plasticity. And I think these Parkinson's patients that got better with the fake injection, they biologically harnessed things. There is a biology there, and if we understand it, and I think part of it is stabilizing these connections that we're making continuously.
So that kind of confidence they may get is almost very much like some type of therapy that reconnects those neurons?
Right.
Just by being happy as opposed to thinking deeply?
Just by being having the confidence and using them, you're stabilizing those connections. That makes you even further integrate with your environment, stabilize more, and one could see this positive, powerful feed-forward system of recovery.
Separate fact from fiction for me, because there are some new studies coming out looking at meditation and specifically transcendental meditation and sort of emptying the mind and how that in fact stimulates the prefrontal cortex. Is this something that we should all be adopting? Is this something that shows promise?
Yeah, I think the area of meditation's a great interest in neuroscience now. The Dalai Lama has visited Stanford several times, and our neuroscience community has embraced that. I mentioned the emerging technology to look at functioning brain circuits in a living person, and the neuroscientists are finding out that those circuit patterns are altered in meditation. So it's a very potent biologic force.
Right, and that includes prayer, because there have been studies looking at functional MRIs of people who are praying, whether they're Franciscan nuns or Buddhist monks, and that it seems to have an impact on the brain.
Well, when you think that what is it doing, if it's essentially shutting down the stress circuitry, then you're changing the biology of the brain, and that stress has been shown over and over again to be an aging product inside of our bodies, and it can be destructive and counterproductive. So if you use meditation or prayer in order to essentially shift away from that, it generally allows you to shift into the bigger picture. You're not focused on the details. You're not hooked into worry, and you relax. And when you relax, it offers an opportunity for creativity and curiosity to come back into your thought patterns of whatever's going on, and it's helpful.
2 points, I think. First, it is known that in animal models, stress actually strips synapses from the hippocampus. So that's very well understood, and it's known something about the biology is actually known about that. And the second thing is that going back to meditation, it's also known that attention and your ability to attend to things and focus on things is also very important for encoding new memories. And so it's clear that if you can meditate, it is a way of shifting your attention and controlling your attention. And one of the major problems, I'm now looking at our expert here in Alzheimer's, is also the attentional problem. That is really part of not remembering is actually not attending. Where did I leave my keys? Well, I don't remember even where thinking about that. So these sorts of skills that we develop, and they're sort of initially unconscious skills, but as we learn about them and attend to them more, we find that this is an important mechanism for remembering, and it may also be important for stabilizing those synapses that get formed.
Curious, what we all had for breakfast this morning, because I know that diet, too, plays a role in brain function, and I want you spoke a bit about the Mediterranean diet. What is it about that helps brain function?
So the epidemiologists tell us that people that eat a so-called Mediterranean type diet, this would be little minimal dairy meats, not strict, same thing the American Heart Association or American Cancer Society would recommend, complex grains, etc., have about a 25-30% less likelihood of developing a dementia during their life. The mechanisms are certainly not entirely clear. There are theories ranging from less inflammation in the body, and inflammation in the brain is thought to be one contributor of demented states. But these types of studies are confounded by the fact that they're passive observational studies. It's possible that people that have a healthy diet also go out and take a run or are less likely to smoke. And so what we really need are what we call prospective trials moving ahead. These are difficult to do. Could you imagine taking the audience here and saying, this half will eat a healthy Mediterranean diet, this half will eat cheeseburgers each day, and then come back in 5 years and we'll examine you.
We need you to do it for 20 years, Frank, because that's how long the effect may take to really...
So it's hard to pin these down, but that's what the epidemiology tells us.
They're all dying of heart attacks over here, so it doesn't...
What about comfort? What about comfort and how cushy your life is? Does that have an impact on the brain? I know the study that I had read is they've taken a series of mice, and they put them in nice soft little beds and endless amount of food that they wanted. Maybe they put the TV on for them, watching some really good things like ABC, for example.
Nice plug, Bob.
And then they would do no exercise. And then other ones they put a little wheel for them to run around. And then they did others that have nothing cushy. They sat on the floor, nothing else, and the exercise thing. And those just on the floor with no exercise, all this to mix them up. And the one what I read was the ones that did the best are the ones who were sleeping on the floor and had no cushiness. Yeah. Now, what is that?
I think we're designed for moderate levels of stress. I think that's what we're evolutionary designed for. But the extreme levels, being in a war situation, etc., and I think Robert Sapolsky here at Stanford is really one of the world's experts on extreme stress, and as Carla mentioned, extreme stress can wipe out neurons in the hippocampus, wipe out these connections. But I think evolutionarily, we're designed for modest levels of stress that probably keep these new neurons forming, keep the connections going. So I think you're seeing a reflection of that. It's the evolutionary perspective is fascinating along these lines, and it also bears on the exercise issue. So when we speak to anthropologists, it's fascinating. Every time I see an anthropologist, I say, well, how many miles were we designed to cover each day? And there's a range. But it's typically 8, 9, 10 miles a day is what we were designed to cover. And that was a basic, fundamental part of our survival. If we weren't covering that distance, we probably wouldn't last too long. And we're probably designed for stress also. So I think the brain is wired in an elegant way to accommodate what we were designed to survive in. And I think that's what we're seeing in those studies.
I guess I just wonder, all I can think about is that if you are living in a life like that and you know other things exist, if you're driven to do something, I would imagine your brain is being fired up, right? The ones that feel they've already gotten there. I know that the biggest source of depression in some ways was the direction of your life, up or down. no matter how much money you have or what your life is like. I think if there's the fact that you're going up, there's a great psychiatrist that wrote a book about it. He traveled around the world to see all the conditions of psychiatry around the world, and he gets on the plane from New York to Paris, first stop. And he'd gotten a coach ticket, and they oversold coach and they oversold first class. So he got bumped up to the business, and he's sitting in this chair, and it's beautiful and comfortable, and he's drinking free wine and everything else. He was so happy. Next to him was a guy who was just depressed because he had bumped down from first class in the business. So you have $10 million and you lost 2, and you only have $8 million left. You're really, really sad. But those that had $12,000 in the bank and they made 1,000, they are happy and ecstatic. I tell kids that.
We know that psychologically, small improvements in your life result in happiness. So if for example, your first car is an old wreck, and then you hit it big, you shouldn't just go out and buy the most expensive Porsche you can find.
Good advice.
You should buy something that is a nice new car, but it's cheaper. Then move up from that, and then move up from that. And what happens is each purchase then induces some happiness. You feel great about each purchase, and you get to stretch out that happiness over years rather than use it all up at once.
But, I see life through the eyes of a parent, and I think those are the lessons that we take away, that the mice in the cushed out room with the video games and the, iPhones were not as well adjusted as the mice who were simply in a spare room with a habit trail. And the ones that were getting exercise were actually doing better. And the ones who start out with the fewer toys and get slightly upgraded have more happiness quotients.
What about music? Go ahead.
Scientists rarely agree on anything, but the one thing we can all agree on is that being a couch potato is no good.
Right. That's a good point. Okay. Music's a great idea because I know, Jill, that you've played guitar your entire life.
I'd like to bounce back, though, and apply that to recovery and rehab because it was true. As we go back and we look at what is attention, and in order to pay attention, your brain has to be able to take this moment and attach it to the last moment, and then you can project into the next moment. That is an enormous feat for neurons to accomplish. And when I experienced my stroke, I didn't have any of that. All I had was this experience of the present moment. Now, it wasn't gone just like that, I have to get a new moment, but it was an experience. And I didn't have that capacity, but you have to have that capacity in order to be able to learn. So for me, it was a matter of I could not remember yesterday the condition that I was in, and I needed my mother to remind me how far I had come because she was keeping the linearity of my recovery. And she needed to remind me. And my mother, everybody says, oh my gosh, this must have been terrible. And they're going, well, no, 1, she was alive. And 2, she was making enormous strides every day, even if she was waking up on her own, or she could roll over, or I could get her to the restroom, or she was awake today, So it was how do you take our information and communicate to somebody in that condition who can't keep track of that themselves so that they can celebrate. And it was that celebration and that joy of, oh my gosh, I'm getting better. And everybody says, Jill, why weren't you ever depressed? And it was because I was alive and I was getting better. I was getting better. And it didn't matter that I wasn't never going to be a Harvard brain scientist again, but it was a matter of, but this is who I am and I am getting better. And then eventually my own mind could come online and give me that information. But it was critically important for my recovery.
I think one of the things we've learned about the human brain is that it is a tremendous learning machine. That's what it really is. And I know my colleagues in computer science, if you asked them 30 years ago, will computers be able to outthink humans by the turn of the century? They would have said, yes, absolutely. And we're not even close. And why? Because the brain is this incredible machine for learning. And if you think about everything that's happening in a day, just being here, just seeing situations occur, you're storing those in the brain. You're learning from them constantly. And Jill mentioned the importance of sleep, because we know that sleep is one of the things that codifies and organizes that learning that occurred in the day. So it's a critical part of that. And that's what makes it really unique.
Yeah, the only thing I was going to say about, ask about music, I ask so many questions. My wife says I'm the most obnoxious person because I ask questions all the time. It's a journalism thing, right?
It is
yeah,
obnoxious.
Neil hates you, I'm sure.
It's true.
Except he's a journalist too, so never mind. But in terms of music, I know that, for example, that music therapy has now starting to connect the right part of the brain with the left part of the brain in terms of plasticity, right? So if you're damaged on the left, which is what Jill, you and I were in terms of the left side, which is largely aphasia, loss of words. If you're hit on the right side, there's like paralysis on the left. There's all, and certainly an impact on music, because music is largely on the right side of the brain. So with Gabby Giffords, for example, who went through the same music therapy, I don't know if you know, I'm sure you probably know, that she was shot right through this part of the brain. They know where it was. The damage to her brain was really restricted. It was just only on that side. It was not on the other side as well. For some reason, she could not remember any words. She lost all of her vocabulary. But when she sang with the guitar, she could remember the words of the songs that she memorized before. So now they think, though, that her playing and continuing to do that, she could actually reconnect some of the neurons in the left side of the brain. With me, since mine was not pierced through an identifiable spot, that mine shaked around, so I lost both of them. So I can't sing any of the songs I used to know perfectly before. I mean, not talking about tone. I'm just talking about words. I couldn't do that at all earlier. But.
Did you play an instrument before?
No, not really.
So you didn't really?
No.
But I'm curious, Jill, your experience, because you played guitar before your stroke, and I know that you continue to play now.
Well, mine has always been self-taught, but I'm a natural musician. I learned cello formally, but I couldn't even tell you the strings on a guitar, but I write songs and I sing. And when I experienced the stroke, one of the things that I was doing, because there's a shortage of brain tissue donated for research into the severe mental illnesses at Harvard, I was the primary spokesperson for the Harvard Brain Bank. And of course, I would go out and I would talk to audiences, and they would realize, oh my gosh, she wants my brain. And it would kind of freak people out. And I would say, well, don't worry, I'm in no hurry. And I'm in no hurry. But I'd pull out...
When they're done with it, then
Exactly. So I would pull out my guitar and I would sing the Brain Bank jingle. And so I was actually having a voice coach, and I went to her and I said, I don't sing in tune. I don't want to be a good singer. I just don't want to embarrass myself in front of 500 people when I'm singing for their brains. And so we were doing that, exactly, like you really cared about that, didn't you? But then after the stroke, I ended up with perfect pitch. And I became a much better singer.
Really?
But here's the weird thing. As my left brain came back online, I went back to being just as bad as I was before.
Oh, that is so hysterical.
But now I don't care.
Well, but we were
That's the
talking-
thing, but now I don't care.
Well, but John and I were talking earlier before we came out. When you learn to ski as an adult, for example, how much of that is fear of falling, right, or learning to overcome that fear, which is something that perhaps children don't, and that sort of ties into: are you better at learning it when you're younger?
Yeah. I think
The answer is yes.
Yes.
You're better at learning it when you're younger, and sadly, it's not just about the fear, and you can do everything you want to conquer the fear, which would be good. But still, the circuits, especially for motor learning, it's just the same thing with like tennis and skiing and all of these, really riding a bike. The circuits for that kind of motor learning, which are in a special part of your brain called the cerebellum, those are also much more plastic during youth. So just like learning a language, motor learning also is much more facilitated early on. That doesn't mean we can't learn. We all, of course, can learn, but it's very different quality of learning.
And yet, what is that trait when once you know how to ride a bike, it can be X number of years and you can get back on that bike?
Well, this is the extraordinary thing. This is the storage property, the ability of our brain to actually, in its circuits, store information that we can later access, even if we haven't used it for a long time. And it's true, it's also true for language. So this is this ability to re-access, and it's part of what I think is a problem in memory loss. So part of it is accessing the old memories. I mean, this business of trying to remember somebody's name, where you knew their name and you used it over and over again, and you remembered it at 3 a.m. And I would love, as a neuroscientist, to know what is going on that finally clicks in and you get that. So part of it is access.
So another issue is that the distribution of the circuits. We were talking about music, and again, having the technology to view circuit activation, one of the remarkable things about music is how many networks in the brain light up with music. So we have dozens of parallel networks in the brain, and certain tasks light up certain networks. But music has a remarkable ability to light up perhaps more of those networks than any kind of input. Why evolutionarily? Who knows? But by being able to activate so many parallel network systems all at the same time, maybe something that can contribute to a little bit of plasticity and recovery. And these distributed networks, riding a bicycle at a young age invokes a lot of networks, so we tend not to lose them. And I see that with my Alzheimer's patients. With Alzheimer's, we could lose the part of the brain in the network that's important for language. So I have one patient that I follow in our Alzheimer center here at Stanford. She lost all ability to use language. She couldn't name any objects, and she lost all of her vocabulary. So her daughter came to clinic one day and said, Mom, sing for Dr. Longo your favorite Frank Sinatra song. She sang all 3 verses perfectly, did not hesitate on a single word. And then when the song was over, I was almost in tears hearing that. I asked her if she could repeat any of the words. She couldn't, if they weren't in the music. And so my thought there is that the music is so well distributed that even if part of those networks are gone, there are enough of them left.
Wasn't it the case in Gabby Gifford's therapy?
Yeah, it's the same thing, but I don't understand. So if she knows those exact words when she sings it, there's something about the tone, the actual notes, that somehow it's attached to that?
And how it's stored. How the memory is stored in the brain and how it's retrieved.
So she could literally remember all those words if she gave a little bit of notes to it.
If it had notes, if it was in her music consciousness, because there's so much redundancy in having multiple systems, parallel networks involved.
Think about it. Try it sometime. Sing a song where you know the melody and the words will come. Try to recite it as if it were a piece of prose, and you'll find it's much harder.
But is it because it's previously attached? What if you wanted to memorize, like right now, I have such difficulty memorizing. I had like a photographic memory before, and I've got like no memory. I can't memorize 3 full sentences. I couldn't be a good actor, I'll tell you that, unless I have a prompter. But I couldn't, so I can't remember those. If I somehow wrote a song with those 3 sentences attached to it, would they connect, or only the ones pre-damaged were connected, therefore I get them back?
I think if you put it in music context, it might be easier to remember. I think that would be an example of a strategic way of remembering.
Okay,
He's going to be the singing journalist.
Right, exactly.
Singing scientist, singing journalist.
You're storing other connections, and I think that's what really makes it. The same thing for these people who can memorize, have 1,000 people walk up to them, memorize their names, and then recite them back.
Right.
They do it by establishing a visual connection between the person and the name. So they store that visual connection, whether it's looking at them and thinking their name sounds like something and imagining something to attach to it.
And what is it we were talking about, recall, the idea that you learn something and then you forget, and then, oh yes, I did know that, I forgot. And so what is it that we can do to help maximize recall? Because there's some research that says when you're taking a hot shower, suddenly it comes to you. You know, there are moments where recall is easier.
You're asking me?
Well, no, anyway, I don't want to put you on the spot.
She doesn't remember.
Because you're a scientist.
I could take... I mean, it's fascinating. So when we store memories, they come into the hippocampus. There's some initial processing, short-term memory. And then the hippocampus does a beautiful job of distributing them throughout the various lobes of the brain. And so they're stored in multiple places, multiple networks. And then to recall them, the hippocampus has to go out and grab that, bring it back into the hippocampus, and then make it accessible to our higher order, our executive function. So in some ways, as we age or in different disease states, the connections between the hippocampus and the rest of the brain aren't as efficient. So that memory is there in the temporal lobe or parietal lobe or frontal lobe. We can't access it as well.
Right, but Juju asked, how do we do that?
So the ways to enhance that we know of so far, short of a drug to make the connections better, during sleep, we have a reverberation back and forth. We're practicing that access during sleep. So one trick would be not to be sleep deprived. Another way is to consciously, with our executive function, come up with workarounds. And that's how we associate something to remember somebody's name. We associate it with something that a visual cue will associate it. So there we're consciously creating an auxiliary connection. We call it association.
If you think about memory, and you think about understanding how the human brain works, if you can't really understand how memory and memory retrieval works, you haven't really got a good hint at understanding the human brain. And we're not even close to really having that deep understanding. And it's much more complicated than the most complicated computer in the world. Because if you think about all the ways we can retrieve something, we see a picture of something, we can retrieve the word, we hear the word, we can retrieve the meaning of the word. It's absolutely amazing.
And we all know that scent is one of the most powerful stimulus for memory.
But I think it's interesting that in this conversation that we've just had, we've kind of revisited our each personal health trick about keeping our brains healthy. I mean, we've heard that exercise is really good. We've heard that sleep is really good. We've heard that meditation and blueberries. I mean, it's a lot of these things really have to do with keeping our ability to remember and to recall really at top form. So it's actually fascinating that, even though these are all things your mother told you to do, go out there and take a run, don't be a couch potato, they have scientific basis as much as we can understand.
Let me ask you, there's one other thing.
I love having you here. Just like you're my wingman.
We work in the same place.
Exactly.
Multitasking, because one thing with me before, I was never good at multitasking, but I did have was an ability to concentrate with really nothing, just not even seeing or hearing anything's around me. But now I'm completely distracted when I try to concentrate a lot. I don't know what it is in the brain that may or may not have caused that. And it also makes me think about the fact that, like my wife, for example, is an amazing multitasker. And I know that I've heard that it's more women are better at multitasking than we are. Is there evidence of some reason for that in the brain? And what may have happened in terms of the multitasking in terms of the brain?
Well, part of the multitasking is part of what we call executive function. It's sort of a higher order function in the brain. And that's thought to largely depend on the frontal lobes. And in humans, it's our frontal lobes that are so well developed compared to other mammals. And so that's the ability to plan, to execute, and to multitask, to have parallel thoughts and manage things at the same time. It turns out in most forms of head trauma, if the brain bounces around a little bit, those frontal lobes can be particularly vulnerable to being bounced around in the skull. So it wouldn't be surprising that after some head trauma, that executive function, the ability to multitask, could be a little bit more challenging. In terms of gender differences, of course, it's just theories and speculation. One speculation is that, again, as we evolved, the male was more singly task-oriented, go find some food, etc., whereas the female was more socially sophisticated, multitasking on many different areas. So again, that's more speculation. It's hard to prove that.
But Bob, there's been recent studies that have shown that people are not nearly as good at multitasking as they think they are, especially young people. Especially young people. And they're sitting there, they're on Facebook, and they're watching the lecture at the same time, and they think they're getting it all in until they get to the exam, and then we find out the truth, right? So people are not as good at this, and I know if I'm writing or I'm doing something really hard that requires a lot of focus, I can't have music in the background. Some people can, but I can't do it. So I think there are limits in how far you go. And if you ever want to see the ability of the brain or test the ability of the brain to multitask, go on YouTube and look for a video called Gorilla and Bouncing Balls. Just do a search for that. And you'll see a video that will prove to you that you're not nearly as good at multitasking as you think you are. The brain really focuses narrowly.
You really should describe the video because it's a classic.
Yeah, so this video, you're asked to watch the video and count the number of times that the blue ball and a green ball, it's a set of people standing around in a circle, and they throw these balls around, and you're told, watch the number of times the blue ball is thrown and the green ball is thrown. So you watch this video, you watch the whole thing, and then at the end, they say how many times. Everybody gives the answer. And they say, what about the gorilla? They say, gorilla? What gorilla? In the middle of the movie, a gorilla comes into the circle, stands there, throws the balls, and 90% of the people who watch the video do not see the gorilla.
But none of those are Stanford students.
Well, no, because they were texting at the same time.
Right, exactly. How many times have I been on my BlackBerry and my son will say something to me and he'll go, Mom, did you hear what I just said? And of course, right over the head.
We always have
You
our-
heard it, but you didn't listen.
Right, exactly.
That's why with brain injury we get this great excuse for everything we want to say.
It's very
My wife would say, "Can you go downstairs and clean up the basement?" I said, "I don't know what a basement is."
Clean! I've forgotten what the word clean means.
It only worked once.
I'm curious, there was something about video games and how older people were taught to play Fortress and how that thickened the neurons in a certain area of the brain. And in fact, video games get such a bad rap. I'm curious, what your thoughts are on this.
So this is a controversial area, and it's related to the area of doing brain exercises.
Right.
So we can buy all kinds of software to do brain exercises. And so a lot of claims along these lines. And it'd be similar to if we play this video game where we exercise our brain, improve these connections, improve our cognition. It's a controversial area because most of the studies, when they've been formally done, have not found much what we call a transfer effect. So you will get better at that specific task. And the question is, will there be much spillover? Will you remember where you parked your car next time, or why you went to the store, or what your grandkid's name is? And most of the formal studies aren't showing much spillover effect. So I think most of us in neuroscience haven't been real impressed, but they're marketed.
And yet, correct me if I'm wrong, but it seems to me that the mice studies show that more nimble building of brain connections are enhanced with exercise. Is that what the mice studies are showing?
Yes, absolutely. But those studies are also focusing on the part of the brain that the mouse was using during the study. So, for example, if the mouse is running on the wheel, then memory is tested in the mouse, and then the mice do better in memory tasks, specific memory tasks. But that's because the part of the brain that's benefiting from the wheel running is the hippocampus, the part of the brain that's important for memory. So as scientists, we're not able yet to really study all kinds of systems as they change simultaneously. So we always are stuck with selecting one part of the brain to study. So we all each are great experts at our own favorite part of the brain. So that's consistent exactly with what Frank said. And this spillover issue is a really big issue, obviously.
Sure.
I have to say that I did use Nintendo games for my rehab, and for me it worked very well. It helped me increase the speed of my thought. It helped me make connections in thought that I hadn't made before. And when I went out into the real world and had to do things like grocery shop or order a rental car, that my brain worked better. So perhaps on the normal brain, it doesn't have that impact, but I can certainly say that for rehab, it was totally effective for me.
I know, well, for one is for sure, coming from my military friends, that those in terms of operating from the helicopters, opening fire, are much better at aiming, coordinating, all of that if they played the games on TV, doing the same thing. What they don't know, of course, is whether there's spillover to something else. It gives an improvement, but without question, there's that. Because when I think about it, maybe with you, with Nintendo, the one that would certainly be very beneficial if it gives you free thinking, right? But if you're just concentrating on one small little narrow thing, I can only imagine that's worse than not doing it because you're taking yourself out of free thinking, which gives you creativity.
I'm curious, Jill, which games you used on Nintendo?
I used the Brain Age games that were out in the Japanese population, and different ones with numbers going in different orientation, and you had to then say how many 7s were there, how many 6s were there, how many red things were there, how many blue things. I did mathematics because I had absolutely no mathematics. For 4 years, people would say, Jill, what's 1 plus 1? And I'd look around and I'd say, well, what's a 1? And they'd say, a 1. They always did this. A 1, a 1. A 1 is everything. And I would think, and I would say, well, if a 1 is everything, how can you have another 1? Right? It made zero sense.
About the universe right now?
Exactly. It was. So for me, those kinds of games got things going quickly. In fact, one of the things that I'm working on now is I just started a not-for-profit, which is all about education, appreciation, and awareness of the human brain for anybody. And we're working on the creation of a video game that is specifically for motor rehabilitation, which is in such slow motion, such boring boring for the normal brain, but for the population, what would I have used in order to be able to get better? And you can't have the bells and whistles, you can't have the lights, you can't have the things, the distractions. You have to be able to have simple so you can focus, and slow motion. First, you even got to get my attention. I need to know you want my attention.
So I think this is a great point, because attention, when you play those games, you're actually learning again how to refocus and use your attention. The rehab for motor, that's again, should really work well, because it's focusing on one modality or a few modalities, including attention, of course. Yeah. And I think if we could understand how these systems normally work, how they're engaged when you're normally functioning, then it might be possible to really design very specific tools and games for learning, for reading, for children, kids that have learning disabilities and so on. So,
or for, as Bob would say, just free thinking, because I have a confession to make. I have this fancy iPad and I play solitaire on it, and my husband's like, I can't watch you doing that, it's like walking into an opium den, and I'm thinking, but it relaxes me and it frees my mind from anything else, and it's sort of a fascinating escape.
Which is switch. You should be doing solitaire, then Sudoku, then something else, just to keep a variation.
Yes, cross-training the brain. There you go.
Brain
cross-training. My kids too, because I know I talk about this as well. Compare the 60s and 70s where I grew up and my kids now, and doing exactly that, driving along in the car and just doing nothing but texting and doing the games and they never look up and they see the sun and they don't look at the leaves. Do we think there's any? What that's doing? There have been studies on texting all the time and all that, right?
Yeah,
which I think has been so far pretty negative.
It's pretty negative.
Right.
Yeah.
People think they're multitasking effectively, but they're not, and I think the results are not very good in terms of that. I mean, the brain's ability. What's remarkable about the brain is this ability to focus on something that can be really, really difficult and hard, and you can focus in there. And when you just bombard it with a lot of different things coming from multiple sources, the attention is divided, and the process of really understanding what's happening with each one of those sources is reduced.
I think what I fear is, I'm sure as a child has practiced focusing on anything, but just focusing on something, I think circuits are being reinforced that are critical for focus on something. And many of us have read about the 10,000-hour rule. If you do something for 10,000 hours, you get really, really good at it. And probably when we're young, if we focus on different things, if we add our total focus time, traditionally it might have been 10,000 hours, and as an adult we're really good at focusing on something. We don't know what it'll be. But what if kids nowadays aren't reaching that level of total hours spent focusing on something? And those circuits, as Carla talked about, it's so critical doing this as a child. What if the circuits of focus are not being developed as children? And every time I see a national survey on SAT results, when this texting generation gets to the point where they're taking these tests and there's a decline in the scores, that'll be remarkable. It'll be too late to change that. But we'll see. That experiment's in process right now.
But hopefully by then we'll know enough about the brain that we can give them all pills.
Get them the circuits
well,
back.
we're going to fix the problem that they all spell without using vowels. That's another.
There's only so much autocorrect. I want to thank you all for being here. I want to give President Hennessy an opportunity to sort of summarize and give us concluding thoughts, and thank everyone for being on the panel and for being here. But John, take it away.
Well, let me first thank our panelists for the wonderful contributions they've made, which is really great. But I think we've seen something else today. We've seen that we are just in the infancy of really understanding this incredible brain that we have that really makes humans different from all the other creatures on the earth. It's our brain that really makes us different. It's incredibly complicated. It's designed to survive incredible traumas, as we've seen in two cases here. And it's designed to provide the lifelong ability for us to learn and to engage in life, to enjoyment, happiness, so many of the things that love. I mean, so many of the things that are treasures. Love is not in your heart, it's in your brain. So on the right side. So we have to remember that, and I think we are at the beginning of an uncharted territory that will take us decades to really begin to understand how this brain works. And from that, I think, will come new treatments for diseases like Alzheimer's and Parkinson's and traumatic brain injury. And with that, we'll all have a better world and a better life ahead.
Now, with that, we're all going to go out and connect to our old memories from here on campus and beat Arizona and have a great weekend. Thank you so much for being here.
Thank you.
Beautiful.
Michelle, that was great.
Beautiful. Thank you.
Reunion attendants, please pick up a